Well, today we're going to talk a little bit about sedimentary rocks. And let's start briefly just with a review of the rock cycle. We're going to go this direction, but eventually we're going to go to the direction of metamorphic rock and igneous rock. But in the meantime, let's start just with sedimentary rocks, or rock cycles. So you all remember the rock cycle. Nature is full of cycles, and sedimentary rocks specifically can be produced from any other rock, including sedimentary rocks. So because it's a cycle, and it's a cycle that has feedbacks going in all different directions, these are, of course, feedback loops, essentially, we're able to produce one rock, turn one rock into another without too much trouble. So, but in order to produce a sedimentary rock, you have to erode, deposit, and then cement sediment. So you break down a metamorphic rock or an igneous rock, and see there's erosion, deposition, sedimentation. That occurs back on itself. Likewise, you can turn a sedimentary rock into the other two by doing it by either melting or applying pressure. And anyway, it's it's a relatively simple cycle, but people get hung up on it being complicated, but it's not. Bottom line, though, sedimentary rocks. One of the main things are these processes that produce rocks, which are called diagenetic processes. So diagenesis, it's a Greek term. Genesis, of course, meaning the formation of something. So any chemical, physical, or biological changes that occur after sediments are deposited, as well as during or after lithification. Lithification is the actual turning of something into a rock, essentially. Some of these diagenetic processes include recrystallization, compaction, lithification, and cementation. Sedimentary rocks that get produced, all these diagenetic processes serve to produce sedimentary rocks, and there's two types, either chemical or detrital. And the big difference, remember, is that anything detrital is made up of fragments of other things. Chemical sedimentary rocks are not. So it's a little bit different. Okay, two completely different sets of diagenetic processes producing these different types of rocks. We'll start with chemical. Here's some salt from a Himalayan salt mine. Most of you, well, every single one of you eat this particular sedimentary rock every day of your life. And we call it, so you can call the mineral form is halite, but the rock form is rock salt. And let's be honest, especially in the winter times, rock salt is everywhere. It's inorganic, so it's not produced through biological processes of any sort. It's an evaporite primarily, so this salt, which came from the Himalayan mountains, at some point was part of a desert wherever the water, there's a certain environment where it would rain and then all the water would evaporate. And that's how you produce it over time. Another example of a chemical sedimentary rock is lithographic limestone. And when you dissolve enough, or when you evaporate enough water, the first thing to start to crystallize is calcium carbonate. We'll get to that in a moment. Here's a playa lake. This is a great example of a place where you're going to get various evaporite deposits. Now there's a whole succession of evaporite deposits. Here's a little triangle diagram here. You start out with a whole lot of water, and all these chemicals are dissolved in the water. But when you first start dissolving, evaporating the water, when you get down to where you have 68% of the water evaporated, you've been that whole time you're producing calcium carbonate. That's where you get lithographic limestone. Limestone that doesn't come from biological processes. Once you get down to 88, between 68 and 88%, the next 20% of water, you're getting gypsum. And then you get to halite. And halite's table salt. That's what you're used to messing with. So gypsum comes first. So here's your drywall product. Here's your halite product. Then you get the bledite, which I'm not all that familiar with. But eventually you get down to Epsom salts. Those are pretty special magnesium sulfate salts. Dead Sea salts, which are people sometimes swear by for health reasons and whatnot. It's a lot of new agey stuff there. And then you get down to this very specialized sea salt, and that's 91. That's when 99.1% of the water is evaporated. That's the thing. That's what's crystallizing out at that point. But this is a whole succession. This is definitely worth knowing something about. Limestone crystallizes out first, followed by gypsum, halite, and so on. So another kind of chemical sedimentary rocks are the bioclastic sedimentary rocks. Now, there's detrital rocks, which are made up of fragments. All detrital rocks are also clastic. Clastic simply means that it's made up of fragments of other things. And it doesn't have to be detrital for it to be clastic. You do have some organic slash chemical slash biochemical rocks that are made up of fragments, such as coal, just decayed plant material, and fossiliferous limestone are both considered chemical sedimentary rocks, bioplastic sedimentary rocks. This just goes through the process of coal formation, more diagenesis. You get this swamp, and there's just the right environment. The plant matter dies and falls into the swamps, and eventually it starts to go through the process of coalification, which is basically a process that gets rid of oxygen. Eventually, you end up with anaerobic decay, and you're mostly just geothermally cracking for gas and oils, and you start to produce the various levels of coal. Eventually, anthracite is nearly pure carbon. Detrital sedimentary rocks are the other type of rock, and those are primarily derived from sediment inorganically. You're familiar with these. These are the easy ones. Shale, sandstone, conglomerate, so forth. You know, the Ridgely sandstone, for instance. And this is a great little image. So this image talks about how you determine how to classify detrital sedimentary rocks, and it's all by grain size. So it starts out with grain size. So if you have large things that are 4 to 6 millimeters in size or larger, we call them pebbles. And of course, there's grain sizes that are above pebbles. So you eventually get the boulders and the cobbles and boulders and things. But anything in these two categories would classify as they're making up a conglomerate. Anything in these three sand categories is considered sandstone. And the Ridgely is kind of like something like a medium to coarse sandstone, somewhere in here. Silt, it feels very smooth, but you put it on your teeth, it's gritty. And so that's a siltstone. And then clay, of course, is very smooth, and you can't really sense the particles. Another aspect of the sediment we like to describe, which helps us say something about where the rock came from and its origins, and well, that is where the rock came from, obviously. I'm repeating myself, but let's say you find a coarse sandstone that has very angular grains. Then you know that it has not gone through, perhaps it hasn't gone through, a whole lot of contact with water. Perhaps that sediment was produced by landslides or rock falls or whatever the case may be, but it didn't. It may have been carried and collected by water in a basin of some sort, but it didn't go through a lot of beating up of water and beating up in a stream with other grains hitting it and things like that. And then we talk about sorting. So an immature sediment is one that's not very well rounded. An immature sediment can also be one where you have, like many conglomerates, a coarse array of sediments, everything from fines to pebbles. So there's a variety of ways we can describe a sediment. And we'll do some of that in class, actually. Fun little lab where we look at some sediments. All right, so which of these is well sorted? That's a question to come to class with an answer from. All right, now there's two other main topics with sedimentary rocks. One is sedimentary environments, just saying that there are certain environments in which certain types of sedimentary rocks get produced. And I think most of these are pretty straightforward. I think we all picture glacial environments, desert environments. We've seen pictures of deserts with sand. We just looked at one with sand. Certainly everybody around here knows what a lake and stream environment looks like, particularly streams, deltas. Okay, those are, of course, where rivers empty into bodies of water, and then ocean bottom sediments. And I'll show you some pictures of these. This is an alluvial fan. So you got mountains, and you got a very steep gradient that flattens out very quickly down into the valley. And so this is what an alluvial fan looks like. It starts out very narrow, and then when the water comes out of this narrow canyon, it spreads out in a fan shape. And it slows down significantly and deposits all its fine material. Yeah, it's a typical ocean environment. This is a beach, a black sand beach on Santorini, where my wife and I first met, essentially. But I've actually been to a beach almost exactly like the same one on the same island. We didn't go to this one, but all right. And then you get deltas. This is the Mississippi, just showing you the various places the delta has been throughout history. The delta does not stay put, although it does now because the Army Corps of Engineers makes it stay put. But you can see, if you pause this, you can read when the delta was in certain places. These are various seafloor environments. I would encourage you again to pause and just admire the various environments down here. Finally, the last topic of sedimentary structures, and these are a structure is something you see in the rock that's not a fossil. It's produced inorganically, and it may tell you something about how the rock was deposited. So these include mud cracks. Well, when you get a clay sediment where the water evaporates relatively rapidly and pretty completely, you end up with these desiccation cracks in various shapes, and they call them mud cracks or desiccation cracks. Ripple marks are indicative of an environment where there was a constant flow of water, so much so that eventually the sediment lithified where it was, and you can actually see the ripple marks preserved, and you can even tell which direction the water is moving. Any guesses? If you said left to right, then you were correct. So the water is moving from over here to over here. Graded beds indicate some sort of a current. Sometimes they're coarsening upward, sometimes they're fining upward. So the fine stuff will be down here and coarse stuff will be up here. So they will tell you something about what kind of an environment you're in and how that sediment was deposited. And finally, cross beds. So here you can see sets of cross beds, and you get these nice angled beds sandwiched between. It's kind of like having a row of imbricated pickles in between two pieces of bread for a pickle sandwich. It's kind of the way I like to think of it because I like pickles and I like bread. Okay, well that's the end of that. I hope you enjoyed it, and we'll talk more in class. Till then, toodaloo.